Good afternoon. My name is Todd Shearer, Senior Application Engineer at Galil Motion Control. Today I will be discussing Galil's ladder interface software. This software converts a standard relay ladder logic program into code for Galil's RIO Compact PLC. In this presentation, I'll provide a brief overview of the RIO Compact PLC and then introduce the ladder interface software. I'll discuss the functions supported by the software and then walk through how to program an actual I/O application using the ladder interface software. Galil's RIO Compact PLC combines analog and digital I/O with intelligent processing in a compact, cost-effective unit. It can be used as a standalone PLC, or it can be connected with Galil Ethernet motion controllers, other RIO units, or even third-party Ethernet devices. Each RIO unit contains numerous I/O, including 16 opto-isolated inputs operating at 5 to 24 volts, 8 high-power sourcing outputs operating at 24 volts and 500 milliamp, which are useful for driving relays and other devices, 8 lower-power syncing outputs operating at 24 volt DC and 25 milliamp. The RIO also has 8 analog inputs and 8 analog outputs. There are two models. The RIO 47100 has 8 analog inputs and 8 analog outputs operating at 0 to 5 volts DC with a 12-bit resolution. The RIO 47120 also has 8 analog inputs and 8 analog outputs, but these are configurable in software as plus and minus 10 volt, plus and minus 5 volt, 0 to 5 volt, or 0 to 10 volt. In addition, they have 12-bit resolution with an optional 16-bit. You can also have them configured for differential or single-ended operation. These are useful for interfacing to analog devices such as temperature sensors, pressure transducers, and fluid pumps. All these I/O are contained in each RIO unit. You can easily add more I/O by using additional RIO units. In addition to the I/O, the RIO provides intelligence allowing for fast processing of I/O events. The RIO has flash memory for non-volatile storage of programs, variables, and arrays. Other features include pulse counters, process control loops, a web interface, email capability, multitasking, and power over Ethernet. The RIO is programmable and accepts Galil's standard 2-letter commands. For example, the command SB1 sets output 1 and CB1 clears output 1. Over 100 commands are provided, allowing virtually any operation to be handled. While programming the RIO PLC using Galil code is easy, some programmers may prefer to specify I/O logic using ladder programming. Galil's ladder interface software converts a ladder program into 2-letter code for input into the RIO. Relay ladder logic is a standard programming format used primarily for programmable logic controllers, or PLCs. It is a graphical programming language where various elements are used to specify I/O logic. This screen shows an example ladder logic I/O diagram. Galil's ladder interface software converts a standard relay ladder logic diagram into deterministic code for input into Galil's RIO PLC. Galil's ladder interface software supports numerous standard relay ladder logic functions, including contacts, coils, control relays, boxes such as timers, counters, and data manipulation, mathematical and logical operators, and analog I/O. In addition, there's a command box to send raw 2-letter Galil commands. Let's look at some example ladder diagrams for various I/O functions. Here, X0 and X1 represent logical, normally open contacts triggering an up counter. Y0 and Y1 represent digital outputs. The up counter operates by incrementing an internal counter by 1 for each false to true transition of the ladder rung. In this case, if X0 or X1 transition from false to true, the counter will increment. A counter also has a preset, represented here by K50. When the current internal counter value exceeds the preset value, the counter done bit, CT0, is set true. The next rung shows a comparative contact. In this case, V250 represents an internal variable location mapped to the current counter value. If that location is greater than the constant value 25, output Y0 is set true. The third rung is similar to the second. If variable location V250 is less than 25, digital output Y1 is set true. The ladder program is then ended with an end rung. This example shows X0 and X1 being used for an on-delay timer. The on-delay timer works as follows. When the ladder rung evaluates as true, the timer begins counting in milliseconds. As long as the rung remains true, the timer is counting. If the rung evaluates as false, the timer is stopped and reset to 0. Additionally, the timer has a preset value associated with it, represented by the constant k. If the rung is true and the current timer value is greater than the preset value, in this case 1000 milliseconds, the timer done bit T0 is set true. So, for this example, if normally open contact X0 and normally open contact X1 are true, the timer will be counting. When X0 and X1 have been true for greater than 1000 milliseconds, the timer done bit T0 is set true. In the second rung, when T0 is set true, the physical output Y0 is also set true. Again, the ladder diagram is ended with an end rung. Now let's build an application with Galil's ladder interface software with the following example. This particular application uses the RIO to scan barcodes as they pass by a conveyor belt. If there is a valid barcode on the package, the counter is incremented and a green pass light is illuminated. If the barcode is invalid, another counter is incremented and the red fail light is illuminated. If a package is flagged as fail, a push bar then moves the package to the appropriate fail location. When developing an application in ladder logic or any code base, a good first step is to plan the code structure in a flowchart of the logic required. Here is an example of that flowchart. Looking at the flowchart, we can see that the code will have the following logic. Read the digital input or contact for the start button. Set the output to begin the package conveyor. Read the digital input for barcode scanner reading passed or failed. Set the appropriate corresponding digital outputs for the push bar and lights. Increment the counters for passed and failed packages. And then start the process all over again. Here we see the ladder interface software program. Across the upper bar we see all of the contacts available to the user. Normally open contact, normally closed contact, and then various comparative contacts. At the end of the rung, we were able to add boxes and coils. Here we see an output coil, and here we see various timer and counter boxes. So let's start implementing our ladder example. The first rung we will add the ladder logic for the conveyor. Again, we want to add a normally open contact, represented by X0, for the start button. When this rung evaluates as true, or that start button is depressed, we want to turn the conveyor on. We'll use a physical output to do that. So we'll add a coil and an output, and we'll call that output Y0. The next step is to add another rung. So we'll insert a row, and this row is going to represent a passed package. When a package is passed through, then we want to insert a normally open contact. In this case, we'll call it X1. And when this evaluates as true, meaning the package has passed, we want to increment a counter. So we go to the end of the rung, and we insert a box. In this case, we want to insert the up counter. For this application, we don't care about the preset, and so we're going to set that to K0. Now, in addition, when a package is flagged as passed, we want to increment the counter and turn on the green pass LED. So we need to have some branching logic here, and we want to set a physical output to represent the green pass light. Since we want just the light to just flash on for one instant, we want to use what's called a positive differential output. The positive differential output is a type of output that will only turn on for one scan of the ladder diagram whenever the rung evaluates as true. And so this output, which we'll call Y1, will come on for exactly one scan each time a package passes. Next, we're going to insert another row, or rung, and this rung is going to represent the failed logic, or the failed package. Again, we need to insert a normally open contact, and we're going to call this one X2. Moving to the end of the line, we also want to count our failed packages. So we insert another counter, an up counter. Again, we don't care about the preset, so we'll set that to K0. And we want a distinct counter name, so we'll call this one CT1. Again, we need branching logic here. And this branching logic is going to allow us to add an output to flash the red failed LED. Again, we'll use a positive differential output so that the output only comes on for one scan. We'll call this output Y2. And then there's a third piece of logic on this third rung. We want another branch to move the pusher bar and push the failed package into the appropriate location. Again, since we only want that pusher bar to move for an instant, we'll use a positive differential output. And we'll call this one Y3. So there we have our entire application in 3 rungs of ladder logic. The final thing we'll need to do here is insert the end rung. An end rung is signified by a special coil known as the end coil. And finally, we want to save this. We go up and we save this application as package.lad. Upon saving this ladder application, the Galil ladder interface software will then output a DMC program. That DMC program is the equivalent 2-letter Galil code that can then be downloaded and run on the RIO controller. Galil's ladder interface software is an easy-to-use tool for converting ladder logic into Galil RIO code. The user graphically enters an I/O routine into the software, which then outputs optimized and deterministic code to run on the Galil RIO controller. With this tool, the entire machine operation may be quickly and easily designed, developed, and implemented. In conclusion, Galil's RIO 471X0 PLC and ladder interface software intelligently handle analog and digital I/O. Please see Galil's website at galilmc.com for more information. Thank you.